Did you know that physicists can be a kind of psychic? Yeah, Forget astrology and all that. If you want to know exactly where you will be 5 years from now, consult a physicist, especially a quantum physicist. He will tell you with very high accuracy, but he will need some information about you, some basic information. It will need to know exactly where you are right now in your situation. But of course, we're not talking about physics insignificant information like your economic situation, your psychology, your education. We are talking about your quantum state. When a physicist knows your quantum state, he can tell you exactly where you will be and when. There is no magic. He can do it by applying some simple formulas. Here we can talk about the uncertainty of quantum physics. I thought nothing was certain. Where were the possibilities? That is correct. Unfortunately, that still hasn't changed. But in quantum physics, as in classical physics, there is a certain determinism or certainty. Yes, we may not know exactly where a particle is, but we can say that it is in a probability cloud. That is, where it could be. As time passes, the location of this probability cloud will change, but we can say where this cloud is likely to be. So we're actually talking about a physical fact here. When you have the quantum state of an object, of a system, even of the universe, that is the position, momentum, spin, and so on, of all the particles at that moment. You can know not only the future, but also the past. Yes, exactly. That's the basis on which physics is based. Without that, the whole system collapses. Then we wouldn't know anything. But there is a very important point here in all this. Knowledge. Yes, I know. Information. What we are talking about when we say the foundation on which physics is based. What we call knowledge cannot be created out of nothing, and it cannot be destroyed while it exists. Information exists and will always exist. And existing information in the universe can never disappear. It will not disappear. It cannot disappear. Because in such a situation, as we said, the system is in grave danger, and the world of physics is stuck in a tremendous obstacle in this regard. The paradox of black hole knowledge. First, let's clarify what exactly we are talking about when we say information. Let's talk about the law of conservation of information. Conservation laws are particularly important for physics and, in fact, for the whole system. For example, according to the law of conservation of energy, energy must remain constant in closed systems. That is, the total amount of energy does not change unless it interacts with an external system. It only changes form. Transformation is possible. So when we think of the universe as a closed system, the energy in it is constant and unchanging. When we apply this to information, that is, the conservation of information, one can get a little confused because we can create information very easily and destroy it in different ways. However, in the quantum universe, all existing information can neither be created nor destroyed. So when you produce information, you are actually only changing the form of the existing information. So with this logic, whether a particle is in an empty box, or in a complex chemical reaction, or in the entire universe we're talking about, physics can change the position and momentum of this system. When we know the spin and the electric charge and so on and so forth, i.e., the state in general, we can predict how this system has behaved and will behave in the past and in the future. In fact, let's push the envelope a little bit to fully understand this information phenomenon. For example, you have a book. In the literature, they usually give an example of a dictionary. You have a thick dictionary, and you burn this dictionary. It's ashes. You have only ashes in your hands. Now the words in this dictionary, all the references, examples, everything, what happened to this information? It's gone too, isn't it? No, it's not. It's not gone. It's not gone. All the information in the book is still there, in the ashes. Yeah, it's a little hard to get that information out. They're still there. They didn't disappear anywhere. I mean, logically, if you take the atoms that come out after they're burned and you organize them correctly, you can rebuild this dictionary. So what we call information is really just a different arrangement of particles. And that's it. As we mentioned in the previous video, quarks and electrons form a rock in a certain order, but when you arrange the same material differently, you get a deer. The material is the same, but the information is different. The rock and the deer is what we call information. Again, when we were talking about black holes, we talked about the fact that for an outside observer, nothing falls into a black hole. We were observing that this object stopped at the event horizon as a result of the slowing down of time. Of course, if this was a space shuttle, for example, the story would be very different for those inside. But let's talk about that separately, because here's what we're going to talk about when we talk about how important it is to protect information. What happens to the information of an object that falls into a black hole? I mean, if it's almost infinite gravity, which we know it is, then there's no problem. So for someone inside the space shuttle, the information of an object falling into a black hole falls down to the center of gravity of the black hole and stays there. For someone looking from the outside, it sticks to the event horizon. From this point of view, there is no problem, because the information is still there. It is not disappearing. We just can't access it. That's all. That's all. Stephen Hawking makes an appearance here. As no scientific discovery can be attributed to a single person, here is Stephen Hawking in Moscow in 1973, talking to Soviet scientists Yakov Zeldovich and Alexei Starobinsky, who told him that spinning black holes form particles, and he would say that he was sort of repelling these particles. When Hawking took this prediction and did the calculations, he would indeed find that not only rotating, but also stationary black holes produce radiation. In other words, black holes had a certain temperature, and with this phenomenon that we call Hawking radiation today, in fact, black holes, like water boiling on a stove, they vaporize and lose their energy and therefore their mass. Black holes weren't really dark at all. I mean, eventually, after a certain amount of time, the black hole would evaporate and disappear at some point. It's worth emphasizing that. It would take billions of years for a black hole to disappear like this. But that's the theory. That's the reality. Black holes die. And this is where the real trouble, the big trouble, comes in. Information could not be destroyed. What happens to a spaceship or stars or anything that falls into a black hole? And what happens to the information they have? Congratulations on our paradox, the black hole information paradox. Because here's the thing, Hawking radiation, whatever you want to call it, it's thermal radiation. So it carries no information, it's a completely random radiation, and all black holes vaporize with a similar radiation, no matter what's inside. So the radiation we call Hawking radiation or mass loss is all about the mass spin in charge of the black hole. It has no other properties. Therefore, all black holes are exactly the same except for these properties. The knowledge of the particles inside is not contained in Hawking radiation. And with this radiation, with this vaporization, one day the black hole will die. And the information? None. Well, I mean, maybe there is. I know it's a dead end. Don't worry about it. It's the same for the scientific world. For almost 50 years, we haven't found a complete solution to this paradox. So have we given up completely? Of course not. There are different theories. If you want, let's take a look at the most popular possible explanations together, and let's discuss in the comments which one makes the most sense to you, or what you think the explanation might be. Now, the biggest problem is this. We knew about the existence of black holes long ago. I mean, we predicted it according to what? According to Einstein's general theory of relativity, of course. Space-time is a curvature in time after all. But we are trying to use quantum mechanics to explain Hawking radiation. We are trying to build a house of quantum mechanics on a foundation of classical physics. But we know that general relativity and quantum physics do not get along particularly well. So to explain Hawking radiation, we need to combine these two revolutionary laws that best explain the universe. This is where another big paradox for the scientific world arises. So before we say, we don't care whether information is lost in black holes or not, we need to look at this scenario. Now, whatever is inside the black hole, whatever it has swallowed and is not giving back, it doesn't matter anymore. Let's imagine that one day it dies and all its energy is expelled by Hawking radiation, and all the information inside is lost, disappears, and that the law of conservation of information is garbage. Do you know what that means? We may have to ignore all the laws we know. We may have to rewrite everything. Knowledge, movement, everything. We might have to rewrite. We've done it a few times in history, but when we've come this far, I mean, it would be a very frustrating finding, but also a very comforting one. And maybe that's how we can make the leap that we need for humanity. Or information is not actually lost. So there is actually information in this radiation coming out of the black hole. In this case, the law of conservation of information is not violated. But here's the problem. For nearly 50 years, we have tried all the math. We have not been able to come up with an explanation close to this, including Stephen Hawking himself. Either there's something we can't see, something we're missing. Or again, the math we have here is not enough. We may have to rewrite something again. Orient if we don't have a solid explanation. We can fictionalize all we want, right? That's why. Maybe we're losing information. The universe we're in is slowly being destroyed by black holes. And it sends all this information, what it takes from us, to another place, another universe. It's like a tunnel, or maybe another time, or from here it is up to your imagination. What happens to knowledge? Where does it go? But what is going on in or near or anywhere in these extraordinary formations is not at all familiar to us. And again, as I said earlier, as we continue to study black holes, who knows how much more we will learn. And in the process, maybe we will need a whole new physics. For this, we will need new Einsteins, new Newtons, new Hawkings. Why shouldn't someone from us, perhaps one of us, be among these names? Why shouldn't it be you? And as always, until we meet again, I'm glad you're here. Love,